can start. So, morning, let's start the second lecture. First of all, let me ask if you have any questions regarding the topics we covered yesterday. Nothing? Okay, so today we will start introducing the idea of inflation, and I will do it explaining how inflation that we will define very soon solves the problem that we described yesterday. So let's start from the horizon problem, which is the one that we discussed yesterday at the end. If you remember, the problem was graphically present in this picture. So here I have the log of a given length, and I plot it as a function of the log of the scale factor. We drew a given scale, let's say a given wavelength of a photon that is propagating the universe, or it could be also the distance between two objects. Okay, and we suppose that this distance is smaller than the Hubble radius today. So here I'm plotting the Hubble radius, h to the minus 1, and let's say that this is the time t0 at which which corresponds to some a0, let's say today, and suppose that this wavelength or this scale is smaller than the horizon today. But then we said that since the Hubble radius has a steepness which is larger than the wavelength, sooner or later this Hubble radius will cross the physical scale, which is going like the scale factor, and the Hubble radius will become smaller than the wavelength. Okay, and we did also an exercise to estimate, for instance, the last scattering surface. We said that in fact this is exactly the case. So in the case of the last scattering surface, you are in this situation. The distance between two photons emitted at the last scattering surface can be larger than the Hubble radius at that time, and that creates this so-called horizon problem. Okay, because the photons that we received in fact have the same temperature, even though apparently during the evolution of the universe they never talk to each other. Okay, so how are we going to solve this problem? In fact, the problem you see, the solution you see already there, because let's see what you can change in this picture. Okay, so in this picture you can say, well, a given distance will go like the scale factor. This you cannot change. Once you write down the Friedman-Robertson-Walker metric, any physical length will always grow like the scale factor, so that you cannot change. Okay, so you cannot change this solid line in a reasonable way. But you can change back in time the behavior of the Hubble radius. That you can do. We know that during the evolution of the universe, the Hubble radius has a different time dependence. We know that it goes like 1 over a square in radiation, 1 over a cube, a to the 3/2 in matter, and so on. So we can try to think how to change the dashed line, and in fact that's not very, very difficult. You just do it by hand, basically. So here, let me draw the same line. So this is the lambda that goes like A. So we start from here. Okay, and here at some point, let's suppose, so this is h to the minus 1. Let's suppose that there is something such that is changing the dynamics of the Hubble radius in such a way, for instance, this is one possible example, the horizon or the Hubble radius will cross the wavelength this lambda again, and will become larger than the physical scale. Okay? Here I drew this behavior like kind of a constant, not by accident, because inflation, as we will see, exactly does this. Inflation is a period where the Hubble radius is in fact constant as a function of time. So you see the solution of the Arisin problem is in this figure. We see photons that have the same temperature. We go back in time. These photons were generated, so to speak, at the last scattering surface. They have the same temperature, even though when they were generated, and we go back to this figure, it looks like that they were not talking to each other. But when you will go back in time, if the Hubble radius becomes again larger than the distance between these two photons, when we go back even farther in time, and the Hubble radius becomes larger than this distance, then at that time you could have a chance that the photons acquire the same properties, the same temperature. Okay? So if this condition which we have is graphically it's there, then of course we understand why the properties of the CMB are the same, because in fact they acquire the same properties during this period. Mathematically, what is the condition that we have to impose? Well, we just have to impose that the ratio between the wavelengths, the physical wavelengths, and the Hubble radius, if you take the derivative, so if we take the d over dt of this quantity, we just have to impose that this quantity is larger than 0. Okay, so meaning that the ratio will increase with time, and therefore, which is basically mathematically this graphic condition here, but we know that lambda goes like the scale factor. H to the minus 1 is a over a dot, and therefore this condition is true if a double dot is larger than 0. Okay? So if there is a period of the evolution of the universe where a double dot is larger than 0, then mathematically this condition is satisfied, and then you can get a situation like this. So this is the definition of inflation. Inflation is a period where the scale factor has the second derivative, which is larger than 0. The universe is accelerated. This condition is not true for radiation or for matter, because if you remember, for radiation, A was going like t to the power 1/2. That was a radiation-dominated universe. For matter, it was t to the power 2/3. And of course, if you take two derivatives of that, you're going to get that a double dot is smaller than 0. The universe for radiation or matter domination is decelerating, not accelerating. Okay? But we are not talking about these phases, therefore we are talking about another phase, and we call it inflation. All right? Is it clear so far? Okay. Very well. So now, let's suppose, for a time being, and this is an assumption that I will try to explain in the rest of the lecture, but let's assume, for a time being, that we are in a period of inflation. Okay, so a double dot is larger than 0. And let's also suppose that the Hubble rate, h, which is a dot over a. So here I want to be clear, it's an assumption, which I will work on, and I will justify it in the following. But let's suppose that this is constant. Okay? And let me call it, I don't know, h star. So if you like, this here, this dashed line, which I drew on purpose, horizontal and constant, is basically my h star to the minus 1. Okay, let's suppose that there is a period of inflation where the Hubble rate is constant. If that is so, you see, I can solve this equation, and I discover that a of t is nothing else than some a star e to the h star t minus t star. So I discovered that if there is a period where the Hubble rate is constant, the scale factor grows exponentially. Okay? This is also called a de Sitter period, when the expansion is exactly exponential. And we will work with this assumption for some time. Okay? So let's see that what happens if that is true. So let me erase here. So first of all, I want to define a quantity which I will use from now on, which is n. It's called the number of effolds. In fact, I should say the total number of effolds. And for me, this is nothing else than the log, this is the definition, is the log of A final divided by A initial, where, what is it? This A final is the value of the scale factor when inflation ends. Okay, and similarly, A sub I is the scale factor when inflation starts. Okay, so those are my two reference values, and then they find n to be this this quantity here. Okay, just the log of the scale factor at the end divided by the scale factor at the beginning. All right. So let me see. Let me compute now what is this n in order to solve the Arisin problem. So I want to compute how long inflation has to last in order for solving the Arisin problem. So let's again draw the same picture. You will see it in many times. So I had this scale factor. I had this Hubble radius. Okay, and we said that the value of the Hubble radius here is h star to the minus 1. So let's see what I have to impose in order for the Arisin problem to be solved. And I want to solve it for my observed universe. So I want to be sure that when we go back in time, the largest distance I can observe, which is my local universe, when I go back in time, so let's say that with my lambda I start with my h0 to the minus 1 at the beginning, okay, so here, let's say that this is t0. I want to go back in time and I want to be sure that this scales become smaller than the Arisin during the Hubble radius during inflation. Okay? If I impose this condition, I'm sure that all the universe today, properly reshifted back, was in causal contact during inflation. So what I have to impose, I take my initial scale, h to the minus 1, okay, and I have to go back. So here, let's say that I have AF, the final value. Here, suppose that you start with some AI, okay. So what I have to do, I have to take my initial scale and I go back to, first of all, to the, I do it in steps. First of all, I go back to the moment where inflation ends. Okay, so I go from A0 today to AF. And then I want to go from the end of inflation to the beginning of inflation. So I go to AI divided by AF. Okay? So I'm going back in time now. And I have to impose that this condition, I have to impose that this guy is smaller than h star to the minus 1. Just to be sure that all my current universe that I observe shrinks down to the Hubble radius during inflation. So I have h0 to the minus 1 here. This is AF over A0, which I suppose I write down as T0 over TF. Okay, I will tell you what TF is in a second. And then here I have e to the minus n, by definition, of the number of efforts. Okay? And this has to be smaller than h star to the minus 1. Now, Tf is a temperature that the universe has after inflation, because of course during this period of inflation, at some point inflation will end and the radiation phase will start. We will discuss that in the following, but let me just define this Tf as a starting temperature the radiation phase has when the radiation era begins. Okay? So from here you see that I have to impose that e to the n has to be larger than what? Than h0 to the minus 1 times t0. I do it in this way. And then I have h star divided by Tf. Okay? So here I know what h0 is. It's the current observable universe. It's a radius, let's say. T0 is the temperature of the photons I observe, so this is also known. We use yesterday 10 to the minus 13 GeV. We don't know these quantities. We don't know exactly what the Hubble radius is during inflation, and we don't know the starting temperature of the radiation phase. Okay? But still, this number I can compute. Okay? So from here, what I get, if I take the log of both sides, I get that n has to be larger than what? Than the log of h0 to the minus 1 times t0 plus the log of the ratio between h star and Tf. Okay? So we said that h0 to the minus 1 is 10 to the 42 GeV to the minus 1. We said that T0 is about 10 to the minus 13 GeV. So from here you get that n, if you do if you take the log of these products of these two numbers, you get a number which is about 60. Okay, it could be 61, so it doesn't matter. This is a number over the 60 plus the log of h star divided by Tf. So what we discover from this simple computation is that you need that the scale factor exponentially grows by a factor of 60, okay, more or less times this log of this number. So this log, in any case, is not going to change very much dramatically, this number. You're not going to get 10 to the 20 from this log. Okay, so let's focus on this 60. So the universe has to exponentially grow by a factor e to the 60 in order to be sure that all the current universe that we observe today was contained in the Hubble radius during the period of inflation. If that is so, the Arisin problem is solved. Okay? Again, let me reiterate the fact that this number, you don't have to get in love with this number, and the number depends on these unknown parameters that depends on the model of inflation you want to work with. But you see it's a number of order 10, 20, 50, 100, depends. Okay, it's not a huge number. To some extent, some people say that inflation solves the Arisin problem, taking the log of it, if you like. So you have a big number, you take the log, and you get a number which is over a unity, let's say, and you solve inflation in this way. You solve the Arisin problem in this way, sorry. Okay, is that clear? What I would like to do now is to show that you get in fact the same number if you want to solve the flatness problem. So let's go back now to the other problem we discussed, which was the flatness problem. And let me remind you the numbers that we had to discuss. In fact, let's draw a picture, which it's also in the lectures. So if you remember, we said that we have, as a function of a, the scale factor, let's say, we said that omega minus 1, which is k over a square h square, we said that today omega minus 1 is over a unity, let's say, and in order to go back in time, we have to scale it properly here, and the condition, so let's suppose that this is T0 or A0. So omega minus 1 here is of order of 1, let's say. And okay, let me amplify, because otherwise I will not be able to draw it. if we go back in time, okay, omega minus 1 at some initial value has to be of order of, if you remember, 10 to minus 64 or something like this, in order to reproduce the current value today. You remember? We did this computation yesterday. Where, again, you don't have to fall in love with this 64. In fact, I thought it was 62 yesterday. We evaluated very roughly. It's a number of order 10 to the minus 60 or something. Okay? So how is inflation solving this problem? Suppose now that there is another period. So if you remember, we used a radiation phase to evaluate to go from there to here. But now we are supposing that there is another period. So let's say that this is the final period of inflation. This is the beginning. We are saying that there is another period which is preceding the period of radiation, where something is going on. And what is going on precisely is the fact that we have to look at this relation again and see how it behaves. And you will see that the omega minus 1 has a completely different behavior, because omega minus 1 is k over a square h square, but the Hubble scale is, the Hubble rate is constant, so I can write down h star square here, because I'm assuming that the Hubble rate is not changing with time. And therefore, from this relation, I know that omega minus 1, let's put an absolute value just to be sure, that the final value divided by the one that has at the beginning, okay, of inflation, this is simply equal to AI divided by AF square. So this is e to the minus 2n. Okay? So what happens is that you start now, so let me call, so that was the beginning, so let me now say that this is the final value that I have to explain, but there is another period where it goes back like e to the minus 2n. You see, this is e to the minus 2n, it goes back to a very, very small value. Okay, so basically what happens here is the following. You start from some initial value, the beginning of inflation, and omega minus 1 drops down exponentially. And in order to solve the flatness problem, you have to be sure that the final value is the one by which you start the radiation phase, 10 to the minus 62, let's say. But now, how did you get the 10 to minus 62? You get it from e to the minus 2n. You see? If I impose, let's suppose that you don't know what is this number, but again, you don't care that much, because in any case, you have in your hands a very, very small factor to play with, e to the minus 2n. If this value, e to the minus 2n, is of order of 10 to the minus 62, roughly speaking, I'm done, because in this case, whatever value initially I have, it will drop down very quickly, and it will reproduce a 10 to minus 62 that you need to start from in order to start the radiation era and go back to a value of order unity. You see? And again, if you put the numbers here, what you get, again, you get n of order of 60. So this 60 is a typical number that is sufficient to solve the flatness problem as well. Okay? Now let me comment something which is very, very important here. This number that I figured out in this by these simple arguments here is just the minimal requirement for a period of inflation. You want to solve the horizon problem starting from your local universe that we observe. You want to reproduce with omega minus 1 of order of unity. But in fact, you don't know if inflation lasts for 60 e-folds. In fact, we will see that it lasts for a period which is much, much bigger than 60 e-folds. If that is so, then what is going to happen? You can guess yourself. Suppose that inflation lasts for some number of e-folds which is much larger than 60. Okay? We will make an example later on. In fact, later on we will see, maybe even today, that in a simple model, the simplest model of inflation you can write, this n is not 60, but is 10 to the 12. Okay? So let's suppose that it's much, much larger than 60. What is going to happen? What is going to happen is that omega minus 1 at the end of inflation is much, much, much smaller than 10 to the minus 62. Correct? Compute e to the minus 10 to the 12. 0, basically, no? So it is much smaller. Then the radiation era starts, and you start from a value which is much, much, much more than 10 to minus 62. Radiation phase will start. It increases. Omega minus 1 starts increasing. But at the end, you won't be able, so the omega minus 1 today, let me put it at 0, so we will be something like some 10 to the 62, because yesterday we increased by 10 to the 62, in order to have a order unity here, times a number, let me put it 10 to minus x, where x is much larger than 62. Much, much larger than 62. So this basically gives you 0. Right? So one of the prediction of inflation, and I will specify what I mean by that, is in fact that omega today that we observed has to be equal to 1. Okay? Omega today has to be equal to 1 within the accuracy of the experiments, because in general inflation lasts much, much more than the minimum required. This statement that I just said is not correct entirely, because, as I said, we don't know the number of e-folds. That depends on the model you are looking at, you are working with. I can construct model of inflation where the number of e-folds is the minimum required, 60. And therefore, omega minus 1 will be of order of a number of order unity. But in general, it is very hard to construct such models of inflation. In general, if you write down a reasonable model of inflation, the number of e-folds turns out to be much larger than 60. And therefore, as a consequence, omega today should be equal to 1 within a very high precision. Okay? Another comment, which is very important, is the following. We said yesterday that omega exactly equal to 1 is a flat universe. Can we say that inflation gives a flat universe? The answer is, depends what you mean by universe. The geometry of it that comes out of inflation is the following. So let me write it here in order to be clear. Inflation does not change the geometry of let me write it down in this way. Does not change the global geometry. Okay? Does not change it. If the global geometry of my universe is the one of the sphere, even when inflation has finished, the geometry is still of the sphere. What inflation does is it changes the local geometry. Okay, so suppose that you start from k equal to plus 1 universe, and you have the geometry of a sphere, which is, I put it very small here. Then inflation is taking place. The sphere gets enlarged by a factor e to the n. Okay, so I have e to the n increase the value of the radius, okay, where e to the n is huge, I take this small ball, I increase its radius exponentially, still a sphere is at the end, but with an incredibly large radius. And suppose that we observed only a local part of this surface, let's say, in this analogy. So here is our h0 to the minus 1. It's our local universe. We can observe only a small patch of it. But therefore, if the radius of this sphere is huge, it's clearly that on the surface, if I want to use this sphere analogy, the geometry of this small portion on the surface, if the radius is very large, is flat. Correct? So locally, inflation is predicting a geometry which is flat. But the global geometry is not changed. If you start from an hyperboloid or an open universe, still open will be. But locally, it will be always flat. Okay? Is that clear, this point? Okay. And now you know that omega minus, in fact, omega turns out to be 1 up to a few percent. So this is one of the predictions of inflation that is tested so far. In fact, the errors will decrease in the next future. And but it's interesting that the central value for the omega is 1, in fact. Yes? To the what? Sorry, Yeah. So if the number of EFOs is much larger than 60, the universe that that at the end of inflation was suffering this period of inflation from the Hubble radius initially is much larger than our current horizon, and it should have the same properties. Okay. So you should think of it as a huge region where we can observe by light only a small part of it, but in fact you expect that the properties outside our current horizon are exactly the same, because what inflation did was to homogenize and isotropize all this patch. Okay. Now there are theories where theories of inflation that go and predict more exotic things, like that there are multiverse, in the sense that there are different patches that even now they are inflating and so on. But those regions are not in contact with us in practice, so they are just separate universes that are not influencing our dynamics. Okay. But I wanted to stress this point because generally it's confusing, and I also want to stress again that this is not a generic prediction of inflation, but it depends on the number of EFOs. Okay, so when you hear people say that inflation predicts omega equal to 1, this is not exactly true. It depends on the number of EFOs. Yes. Say it again. Sorry, I didn't understand the question. Yeah, that's a good question. It's a subtle question. Inflation does not. I mean, when you take a Hubble radius, it will expand. At some point, inflation will end. There will be many Hubble radii. Okay, they do not stop exactly at the same time because there are perturbations, in fact, and this is the subject of the few lectures to come. Yes, but I will expand about this later on if you allow me to do, because it will be more clear in the following. Yes. Okay, so other questions? No? Other curiosities about this? Yes, it is close. Globally, it is still close. If omega is large and if k is plus 1, it will be still open if minus 1 is the value of k, and flat if k is equal to 0, which is the simplest possibility. But yeah, globally the geometry does not change at all. Okay, so let's let me see if I forgot something interesting to say. Yes. Maybe another comment that I can tell you, another interesting point to stress. If you remember yesterday, I was trying to convince you that one has to distinguish between two concepts, the particle horizon and the Hubble radius, if you remember. And in fact, while during the period of radiation and matter, the Hubble radius, h to the minus 1, and the particle horizon, rh, are basically the same quantity up to a coefficient of order unity, during inflation, these two quantities are completely different. They are exponentially different. So let me go back to this, because I think it's interesting to see. The computation is rather simple. So let's compute the particle horizon during inflation. If you remember, we said that this is a of t times the integral in dt prime divided by a of t prime. And here I start from some t initial, let's say beginning of inflation, up to some time t. Okay, so here, by definition, this is, let me write in this way, e to the sub I, e to the h star, t minus ti, times the integral between ti and t of dt prime. And here I have a initial, and let me put it here, e to the minus h star, t minus t initial. Okay? Let me erase here, otherwise it's confusing. So now it's just a matter of computing this simple integral. So the AI goes away as usual. So here I have a h star t minus ti, and here I have minus 1 over h star. Okay, and then here I have e to the minus h star t minus ti evaluated between ti and t. Okay, so let me go here. So this is minus 1 over h star. And here what I get the following. I get, when I multiply this guy and evaluate the t, I get 1. Okay, minus e to the h star t minus ti. Okay, and if this guy is large, of course, I will get that this is of order of 1 over h star e to the h star t minus ti. You see, the particle horizon in this case is much larger than the Hubble radius, which is the inverse of h star, exponentially larger. Okay, this is one of those cases in which the horizon problem is solved, because you say, okay, I have a scale which is smaller, it's larger than my horizon at some epoch, let's say the scattering surface. But so you might say, well, there is an horizon problem, but in fact, inflation, what it did, created a particle horizon which is large, I mean, very, very huge, and therefore the horizon problem is solved in this way. So mathematically, you see it also looking at this expression. Okay? So that is what I wanted to tell you as a last comment. Okay, so the next step will be to go back to my assumption, where I assume that h star was a constant, so the Hubble rate was a constant that I call h star. Now I want to try to motivate this assumption. I want to go back and try to understand what are the conditions by which I can impose such an assumption. Okay, so maybe it's a good time to take a 5 minutes break, if you like, and we will continue in 5 minutes. All right, 5, 10 minutes, 5. Let's say 5. Otherwise, we'll go on too much. All right, good. Is everybody back? Okay, Marco is there, so that's okay. All right, so let's continue. So we discover that inflation is a period where A double dot is larger than 0. Okay, so the question I would like to discuss or answer during the rest of this morning lecture is the following. What are the ingredients that I have to use in order to get such a period? So let's go back to the equation that we wrote yesterday, A double dot over A equal to minus 4 divided by 3 pi g newtons times rho plus 3p. If you remember, rho was the energy density of the fluid that I have put in my universe, and p was the pressure density. So from this relation, you see that if I impose that A double dot is larger than 0, then I get that this is true only if P is smaller than minus rho over 3. Okay? So a period of inflation implies, if I realize it by a simple fluid, implies that the pressure of this fluid, whatever it is, has to be, first of all, negative, but also has to be, in absolute value, large enough to satisfy this condition. So from here, I automatically get that radiation won't do it, because P is equal to plus rho over 3. Matter won't do it, because the pressure for matter is basically 0 for non-relativistic particles. So it's clear that I have to introduce something else. I have to do some more gymnastic to get this relation. Okay? Now, the simplest one we will focus on is assuming that there is a scalar field. Okay, and we want to understand which are the conditions on this scalar field in order to have it driving inflation. Okay, now before 2012 it was embarrassing to speak about a scalar field because we didn't know the existence of the Higgs. Now luckily we know there is at least one scalar field in high energy physics. And one reasonable question is, can I identify the Higgs to be the scalar field we will discuss for the rest of the lecture? This is of course not well known. Some people believe that it might be the Higgs. But for today, I would like to assume that a generic scalar field that I will call phi, which is a function of x and t in general, and without too much fantasy, I will call it the inflaton field. Okay? So in the usual jargon, the inflaton field is the field that is driving inflation, is responsible for the period of inflation. Okay, so we have the inflaton field. Let's write down the action for it. So it's the integral in d for x, the square root of minus g, that I have to put because my space-time is curved. And here I use this convention. I write it as minus 1/2 g mu nu d mu phi minus v of phi. So I also introduce a given potential for this scalar field, and this is the action. Okay? Now, out of this action, I can compute the energy momentum tensor, which is minus 2 divided by the square root of minus g of the variation of the action with respect to g mu nu with the indices up. Okay? And if you do the computation, it's rather easy. You discover that this is nothing else d nu phi plus g mu nu times the Lagrangian. Okay? Where by the Lagrangian I mean the piece which is inside the square brackets. Okay? So I guess this is very standard stuff that most of you have seen, right? So I'm not spending too much time in deriving this formula. All right, so now, from now on, I will also make another assumption, because I want to see what is the background evolution of my system. So from now on, I will consider only the phi 0 of t. So I will only consider the classical value of phi. Okay, if you like, if you don't like, you can think of it as the average of the phi of x and t over some given volume. Okay, so I'm only interested in the time dependence, not the space dependent part of the scalar field, because I want to look at the background evolution of my system. Of course, the rest of the lecture, starting from I guess tomorrow, will be devoted to analyze what is happening when I look also at the variation of my dynamics point by point. But for the time being, let me just assume that my scalar field is a function of time, and in order to remind myself about this, I put a 0 here. Okay, this is a convention that I'm using. Some people put a C for classical, but that's not relevant. Okay? Okay, very well. So let's also remind ourselves that T mu nu for its in general is the diagonal part of this. It's a 4x4, but its non-vanishing values are only along the diagonal and are the following: rho, p, p, and p. Okay. And if you combine this definition with this definition, you do it, you compute the 0, 0 component and so on. What you're going to discover is that the energy density associated to this particular configuration is 1/2 phi 0 dot square minus v of phi 0, and the pressure, sorry, plus of course, and the pressure is 1/2 phi dot 0 square minus v of phi 0. Okay? Okay, very well. So from here, you see that I have a chance to get a negative pressure, and that's the reason why people consider a simple scalar field. Because if I compute P over rho, this is 1/2 phi dot 0 square minus v of phi, divided by 1/2 phi dot 0 square plus v of phi. And if phi dot square is much smaller than v of phi, which I'm supposing to be positive in this relation, if this condition is satisfied, then P divided by rho is of order of -1. So you see from these very simple arguments, you see that if I have a scalar field and this scalar field is moving very slowly in its potential, then the pressure is in fact negative, and it can be as negative as -1. Okay, it won't be always exactly equal to -1, because of course phi dot 0 square is not exactly 0, but it will be, we have a chance to make it very close to -1, and therefore the scale factor to grow exponentially as we were assuming before. Okay? Clear? Questions about this? Okay, so now let's be a little bit more quantitative and let's discuss what this condition is telling us. Okay? First of all, let's find the equation of motion of this system. So we will keep the action here, and you know that the equation of motion are simply the derivative with respect to x mu of the variation of the Lagrangian with respect to the mu phi. Okay, minus the variation of the Lagrangian with respect to phi equals 0, okay? So be careful that in this relation the square root of minus g is inside, okay? So if you're only interested in the phi 0, what you get from here are the following equation: phi double dot 0 plus 3h phi 0 dot plus v prime of phi 0 equal to 0. Okay? So, for instance, where this 3h comes from? Where it comes from the fact that the square root of minus g, remember that the metric is minus dt squared plus a squared. So you get the minus g is a to the 6, you take the square, is a cube. And when you take the mu equals 0 here, you have to take the derivative with respect to time of a cube. This gives you the 3 times a dot, which you recognize the h here. Okay. So that is the equation of motion of a scalar of the background of the scalar field, which is moving in a curved space-time whose Hubble rate is equal to h. Okay. All right. Now let's suppose that this condition is correct. Okay, and let's elaborate a little bit, starting from that equation. So we are working under the assumption that goes under the name of slow roll. So slow roll means that this field is moving very, very slowly, is rolling down its potential, but very slowly. If that is the case, so if this condition is satisfied, and we will quantify better on this condition, I can drop, in this equation, I can drop the phi double dot, because the field is moving very, very slowly. So I say that, in fact, this equation is friction dominated, as people say. So it's 3h phi dot equal to minus v prime as a function of phi dot. Okay? So the field is moving with a velocity which is very small. The acceleration, it's even smaller. And we will work under this assumption. Okay? So that is the friction dominated part of the equation that people use all the time under those assumptions. So let me now be a little bit more quantitative about this. So first of all, what does it mean phi dot square much smaller than v of phi? 0. Okay, so what condition does it impose on the potential? So from here, you see, I can derive what phi dot is, and I can plug it in this condition here. So from here, I get that phi dot square is equal to v prime square divided by 9 h square. Okay, and this has to be much more than v. So from here, I know that the kinetic energy is much smaller than the potential if I have this condition, v prime over v square, much smaller than h square. Okay? From here. So you see, you start already understanding that something very intuitive. The potential must be quite flat in order for the kinetic energy to be negligible. And in fact, if it is exactly flat, phi dot will be 0 identically. So it makes a lot of sense that this condition has to be written in this way. Now, in order to quantify better and to in fact relate something to the observations, we introduce some slow roll parameters. Yes. Sorry, h square, so, sorry, it's v. It's v here. So it's the first one is here, and here it's a v. Good. Okay. H square, I can make another, because in my mind I was making another step where h square I write it as v, because it's 8 pi g newtons rho, which is v. I was already making this assumption, but you're right, it's a square only here. So parameters. So first of all, I introduce the epsilon parameter, which is by definition minus h dot divided by h square. In the previous part of in the first part of the lecture, we assumed that h was constant, if you remember. So if h is not exactly constant, but is changing even though slowly with time, you expect this parameter to be smaller than unity. And in fact, you can show that combining the Freeman-Robertson-Walker equation, you can show that h dot is in fact equal to minus 4 pi g Newton times rho plus p. Okay, which for the scalar field becomes minus 4 pi g Newton times phi dot square. Okay, this is an exact relation. I am not making an assumption here because rho has a plus v and p as a minus v, so the potential disappears. And from here, you see, I can write down this as 4 pi g Newton phi dot square divided by h square. Okay? But you remember that h square is, under the assumption that the kinetic energy is small, is of order of 8 pi g Newton divided by 3 times v. So you see, this h square goes like v. So in other words, this relation tells you that the kinetic energy divided potential has to be small. So this is a good parameter to justify the zero conditions. Okay. In fact, we can write it down better. This relation we can in fact compute in terms of the potential. And epsilon becomes equal to 4 pi g, so let me rewrite the relation, phi dot square divided by h square. So this is 4 pi g Newton, phi dot square, divided by 8 pi g Newton divided by 3 times v. So you see that g Newton goes away, the pi goes away. Okay, so I have a factor of 2 here, so I have a 3/2 phi dot 0 square divided by v. So you see this epsilon is the parameter that if it is small, it tells you that the kinetic energy is smaller than the potential. Okay, so it's a good parameter to work with. Notice also that since h is equal to a dot over a, if I take the derivative of this relation, I have h dot equal to a double dot divided by a minus a dot square divided by a square. So from here I get that a double dot divided by a is equal to h dot plus a dot square divided by a square, which is nothing else than h square. Okay, but h dot we said that is equal to minus epsilon h square. So you see I get 1 minus epsilon h square. So you see epsilon, so inflation is taking place when a dot is larger than 0. So inflation is taking place when this parameter epsilon is smaller than unity. Okay? So when epsilon becomes unity, inflation stops because a dot changes sign. Okay? So that's also an important parameter to say when inflation ends. This is not true for all models of inflation, but for a large number of them it is. Okay, so this is the parameter epsilon. There is another, so please keep it in mind. Keep also in mind that this parameter epsilon is changing with time. It's not just a number. It's changing with time when the evolution of the scalar field is taking place, because both phi dot and h square are changing, of course. And we can also introduce another parameter which justifies the equation that I've been using so far, because I've dropped the second derivative of the scalar field. So let's go back here. There is another parameter I want to introduce, which is called delta. at least in my notes I call it delta, it's defined to be minus phi dot double dot 0 divided by h phi dot 0. Okay? And this parameter has to be smaller than unity in absolute value if I want to neglect in the equation of motion the phi double dot. Okay? Now, if you use this equation to compute this relation, you're going to discover that this delta is equal to another slow roll parameter, which I'm going to define now. It's a second derivative, is eta parameter, is a second derivative of the potential with respect to h square, okay, divided by h square. And it's a simple computation that I'm not going to do it now, but if you use this relation, you take one derivative, you go on, you compute this ratio, you're going to get that this delta is equal to the second derivative of the potential divided by h squared times 1/3 minus epsilon, where epsilon is defined in this way. Okay? It's a simple algebra, I'm not going to do it. Now, why I'm insisting about these roll parameters? I'm insisting about that because we will see tomorrow, starting from tomorrow, that the predictions for the cosmological perturbations that come out of inflation, they are expressed in terms of these roll parameters. So you can connect these roll parameters to observables. Okay, so if I want to make a theoretical prediction of some properties of the perturbation that come out of a period of inflation, they will be expressed in terms of these quantities, which are expressed in terms of the potential V. So you start already seeing the logic. You pick up a model of inflation you like. What does it mean? Basically, to pick up a potential, V of phi. You do all your computations. You compute this parameter epsilon, you compute this parameter eta, and therefore delta, and so on. Those you can compute by hand, I mean, given your model. And once you computed them, you can relate them to observables. Okay, the observable will be measured in experiments, then you can go back and compare to your prediction and see if your prediction is correct or wrong. So those parameters are not only parameters that you use in order to see if the roll is attained, but it's something more than that. So please keep that in mind. Okay? All right. Another important observation that I would like to do is the fact that this parameter I told you, they are function of time, but they are changing with time very, very, very slowly. Okay? And you can show it easily. For instance, let's take, okay, so let's write down epsilon equal to 4 pi g Newton times phi dot 0 squared divided by h squared, and let's take the time derivative of it. Okay? So I take epsilon dot equal to 4 pi g Newton. Here I have 2 times phi double dot divided by h squared. Okay, plus the piece that comes from the h squared. But let me just make the argument. And you see here that I have a phi double dot times a phi dot. Okay, so I can multiply by phi dot square, for instance, something like this, and I multiply by phi dot square here. And you see, you start already, well, in fact, by phi dot is enough. You start already recognizing that the phi double dot divided by phi dot, you recognize the delta. Okay? And the phi dot square is the epsilon. So you see, this is of order of epsilon times delta. So it's second order in this roll parameter. So the time derivative of the roll parameter, it's a roll parameter itself, but it's in fact the product of two of them. So we say it's second order in these roll parameters. And since these roll parameters are small, you can, in first approximation, neglect the time dependence of that. Okay? All right? So you see, the correct statement is that these epsilon are time dependent, but it is a good approximation to assume that the time dependence is negligible, even though there is a time dependence because it's second order in these roll parameters. So from now on, I will work only at linear order in these roll parameters to make a connection between the prediction, the theoretic prediction and the observation. Of course, in the literature, you will see a much more involved computation that goes beyond even the second order in this roll parameter. That's not the point. Of course, the more accurate is the measurement, the more terms in the expansion you need to take. Okay, but for the sake of this lecture, I will drop the higher orders. Okay? Yes? Yeah, but this S square will give you an H dot. The H dot gives you an epsilon, so you are going to get an epsilon square from here. You see, so it's the same thing. Okay? All right, so let me... So let me just draw a simple figure, just to get so the idea. So we have a potential V of phi 0. Here I'm plotting with respect to phi 0. I have a potential which is extremely flat. So here I have my scalar field, which is slowly rolling down towards, let's say, a minimum of its potential. So inflation is taking place. So at any time, so let's say the inflaton field is here, is there, blah, blah. At any time, I can compute my epsilon parameter and check if my epsilon parameter is smaller or larger than 1. If it is larger than 1, inflation is over. At some point, let's say that my potential is something like this. Of course, at some point, the inflaton field will start rolling down very, very quickly towards the bottom of its potential, and there the kinetic energy will be large. So it's clear that in that stage, inflation is not attained. But if there is a plateau which is flat enough, then inflation is taking place in that region. Okay? So that is more or less the picture that we have in mind. But the take-home message is that the potential must be quite flat in order for inflation to be obtained. Okay, so now let's take a generic potential and compute the number of e-folds that we were discussing before. Okay? So the definition of the number of e-folds is, as we said, was the log, if you remember, of the scale factor at the end divided by scale factor at the beginning. But in fact, the true definition of the total number of e-folds is the integral between Ti and Tf of h of T prime in dt prime. Of course, if h is constant, you're going to get the same definition as before. Okay, but this is the more rigorous one. Okay, so the total number of e-folds is the integral between the initial, the beginning of inflation and the final value of inflation of the Hubble rate, which now is not a constant because you see the potential is not exactly flat. So when the inflaton field is going down, the value of the Hubble rate is changing. It's not changing that much, but it is changing. And then I have to integrate over time. Okay? So now in order to compute this number, given a model of inflation, what I do the following. I integrate it again, but I change my variable now. Instead of taking dt prime, I take dt prime over d phi 0 times d phi 0. So I want to trade my time coordinates with my inflaton field. Something that I can do if I have only one degree of freedom, because at any given time, the value of the scalar field is given. If the dynamics, if you know the dynamics. Okay, so I have this thing, but then what I have the integral. So here, in fact, I should change. I take phi I and phi final of h. Here I have divide by phi dot 0 times d phi 0. Okay, so this computation, as you see, is very simple. There is nothing deep in it. But now I want to use the roll conditions, and I want to replace the, I want to use the following equation, 3h times phi 0 dot is equal to minus v prime. Okay, so I write that n is equal to the integral between phi initial and phi final in d phi 0, that I keep it at the beginning. Then I have h divided by phi dot, which I write it from here, is minus v prime, and then here I have 3h squared. Okay? Now I know that h squared in first approximation is equal, so first of all I get rid of the minus sign, changing the order of the extreme of the integral. So I integrate between phi f and phi initial in d phi 0. So I got rid of the minus sign here. 3h squared, I write it as 3 times 8 pi g Newton divided by 3 times v, because the kinetic energy is negligible, divided by v prime. Okay, so you see the 3 goes away. And then I have simply that my total number of e-folds is the integral between phi final and phi initial of d phi 0 of what? Of 8 pi g Newton. And then I have v of phi 0 divided by v prime of phi 0. Okay? I hope you can see from the bottom. So you give me a model of inflation. What you have to do, you pick up your preferred potential. You have to compute the initial value at which the inflation is taking place. You compute the final value, but the final value is easy because epsilon has to be equal to 1. You do a simple integral, and then you compute the number of e-folds. Okay? That is the rule. So this is a very generic formula that you can use all the time. So let me do an example. Let's take the simplest model of inflation we can think of. V of phi 0 equal to m squared divided by 2 phi 0 squared. Okay? A free scalar field with a given mass m. No interaction whatsoever, and so on. Okay? So, all right, very well. So what is the total number of e-folds? Is the integral. Well, let me put the 8 pi g Newton outside. So it's 8 pi g Newton times the integral between phi final and phi initial in d phi 0 of what? Of I have to compute v, so I put m squared divided by 2 phi 0 squared divided by the first derivative, which is nothing else than m squared phi 0. Okay, so the m squared goes away, and here you have 4 pi g Newton, because the 8 goes away with a factor of 2, integral between phi final and phi initial of phi 0 in d phi 0. Okay? So here I get 1/2. So I get 2 pi g Newton phi initial square minus phi final square. Okay? Very simple expression. Okay, so let me change the blackboard, otherwise it will become a little bit complicated. Okay, so now we want to compute what is the value of phi final, for instance. Let's do this exercise. So we said that phi final corresponds to the moment where epsilon is equal to 1. Correct? On the other side, we said that epsilon is equal to 4 pi g Newton times phi dot square divided by h square. Okay, so from here I rewrite as 4 pi g Newton. Phi dot, I again use the following expression. Phi dot times 3h is equal to minus v prime. So I replace it here, so I get v prime square divided by 9h square. Okay? And here I have another h square. Okay? Alright, so far so good. So then I have 4 pi g Newton divided by 9. I rewrite the v prime square, and here I use the fact that h square is equal to 8 pi g Newton divided by 3 times v. Okay? So from here I have to take the square of it, so I have 8 pi g Newton, okay, divided by 3, everything square, times v square. Okay? All right, so you see, okay, let's see if I have a 3 square and a 9 here, this goes away. I have a 64 here. So, did you follow? Is it correct, the computation? I believe it is, no? I think it is. So I have, let's compute the coefficient, so let's do one passage more. I have 4 pi g Newton, I have v prime square, okay, and then I have divided by, the 9 has gone, I have a 64 pi square g Newton square times v square. Okay? Something like this. Okay, very good. So I want to, no, this I can erase. And now I need to impose that this number is equal to 1. Okay? So what is v prime divided by v? So as we said, this is m squared divided by 2 phi 0, m squared phi 0 divided by m squared divided by 2 phi 0 square. So the m squared goes away, so here I have 2 divided by phi 0. Okay? I have to take the square of it. So epsilon, I read it is 4 pi g Newton divided by 64 pi square g Newton square, which I can eliminate here, g Newton. Okay, and then I have 4 divided by phi 0 square. I want this to be equal to 1, so you see I can find the value of phi f, in fact, phi f from here. Okay, so I have 1 over, here I have 1 over 8, this becomes a 2. Okay, so phi final square is nothing else than 1 over 2 pi g Newton. So you see, phi, since g Newton is 1 over m Planck square, phi final is of order of m Planck. So you see, these kind of models that go under the name of chaotic models, they are dominated. You get inflation when the scalar field is in fact of order of m Planck. This is the reason why they go under the name of large field models. Okay? Okay, so this is phi final. What is phi initial? Well, for phi initial, we don't have the same logic to follow. We cannot compute it. We can just assume or give a reasonable assumption of what it is. So let's make a simple assumption, because, in fact, this is what was written at the beginning by Linde, who was the proponent of this kind of class of models. So I know that the potential is m square divided by 2 phi 0 square. So how can I judge what is the beginning, what is the value of the scalar field at the beginning of inflation? Well, let's be brave and assume that this is of order of m Planck to the 4th. Okay? What is the logic behind it? Well, we say that inflation, I mean, there are, during this early universe, there are fluctuations. Those fluctuations will push the value of the scalar field to along this plateau to very large values, and the largest value you can think of for the potential is the largest energy you have in the problem, which is m Planck to the 4th power. Okay, of course this is just an assumption, but let's go for it. So from here you get the phi initial square will be of order of m Planck square, to the 4 divided by m square. Okay? Now, in the rest of the lectures, not tomorrow I guess, but the day after tomorrow, we will discover that this parameter m is fixed by imposing that the perturbation that you get out of this model are matching the observations. And you have to just believe me for the time being, but we will come back to this point, as this number is of order of 10 to the 13 GeV, 10 to the 12 GeV, let's say. Okay? So it's much more than M Planck, which is 10 to the 18 GeV. So from here, I get that this guy is, in fact, much larger than phi final square, which is of order of M Planck square, if this condition is true. So what I get, looking at that expression, I get that the number of e-folds is of order of 2 pi g Newton times phi initial square. Okay, but g Newton is 1 over M Planck square, so from here I get the total number of e-folds is of order of M Planck to the 4th divided by M square divided by M Planck square that comes from this g Newton. So it's of order of M Planck square divided by M square. Okay? And if that is the number that I have to choose, I have basically 10 to the 18 divided by 10 to the 12 is 10 to the 6 square. I get 10 to the 12, which was the number that I was mentioning before. You see? So if this model is correct, in fact it seems to be already ruled out by the data unless you do some more gymnastic on it. If this model were correct, then of course the number of e-folds will be huge compared to the 60 that I was mentioning before. Okay? And therefore this model would predict that omega is extremely, well, it's basically 1 omega today. Okay? Up to an error which is infinitesimally small. Okay? Now you can repeat the same kind of arguments for any model you like, but the computation will go through the same line. Okay, so you have to compute the integral, you have to compute the extrema of the integral, and then you compute the total number of e-folds. That's the logic. Okay? And I promise you, you're going to get most of the time a number which is much larger than 60. This is a simple example. I believe in the exercises there is another typical example that you can do in order to convince yourself that that is the case. Okay? All right, yes, please.
So do we understand this? Why we always get something much larger than...
Yeah, to some extent, yes, because you see, when you look at this integral, you have, if you rewrite this integral in terms of epsilon, the resolve parameter goes like 1 over the square root of epsilon. And the epsilon usually in these models is extremely small, and therefore the integral is large. Yeah. But it is related to the flatness of your potential at the end of the day. So the flatter the potential is, the larger is the number of e-folds that you get out of it. This is more or less true. Okay? Yes?
So when you say that some people believe that the Higgs could be the is it within a different class of models?
Yeah, so if you take the standard model of weak interactions, and you take a potential that is the usual one with maxing get and so on, you can show that inflation is not taking place in this simple model. Why? Because the potential is not flat enough. Unless you do you go to some particular region of the Higgs potential at very large values of the fields where maybe there is an inflection point and so on, but you don't get enough e-folds in this case. So, yeah. So what you have to do, you have to couple in the standard model to gravity. You couple it, in fact, using a renormalizable coupling. So it's you can do it. What you do in particular, you couple through a coupling constant psi. You couple the Ricci scalar, which during inflation is 12h squared times the Higgs square. Okay, this is dimension 4, so it's okay. There is no problem with renormalizability. But you can show that if you go through the same kind of computation and you also fix the perturbations, which is something that we haven't done it yet, but we will do, this psi parameter has to be huge, 10 to the 4. Okay. Also, there is nothing wrong with that. but this is the outcome. Okay, so in principle you can do it using the standard model of weak interactions. Some people criticize this kind of approach because it looks like that, you know, you are very sensitive to corrections that on the standard model effective potential. So there is a lot of debate about this, but this is the state of the art. So to answer your question, the answer is yes, you can do it, but you need some steps.
And the mass that is required to fix the oscillations, is it of the same order of the mass we measured for the Higgs, or is it?
No, because the mass of the Higgs, the 126 GeV, is the curvature of the potential at the electroweak vacuum. When you do inflation, you're looking, using this trick, you're looking at a completely different part of the potential. There's nothing to do with our vacuum today. So the mass there is different. It's not of course, I mean, you can relate your prediction to the mass of the Higgs because you have a running of the coupling constant. So, you know, you fix the running, you fix the boundary value today at 126 GeV, then you run a lambda, blah, blah. But that's a very indirect way. But to answer your question, the curvature of the potential has nothing to do with the curvature at our current vacuum. Okay. So, I mean, there is a lot of activity of model building for inflation. I mean, 30 years of activity, but luckily now we have a bunch of data and we can make predictions which are generic enough. But of course, once you have your preferred model, you should work with that. Okay. So let me ask if there are any other questions for this. Yes.
Why do we need a flat pressure? So we said that we need a negative pressure, right?
Yeah.
That's, I can still have some kinetic energy.
Yeah, of course. So the correct condition as P is more than minus rho over free. As long as you are in that regime, that's okay.
So that would not have a very small epsilon and therefore not.
Yeah. In fact, you know, P is equal to minus rho when you are, you know, in the large, for this model, for instance. But then, of course, the moment where you go down, then of course this condition epsilon goes to 1 means exactly this boundary that I just said. So, I mean, usually because you want to get some number of e-folds large enough and so on. So it's, but I agree, the boundary is this minus 1/3 in terms of the equation of state. Yeah. Yes, please.
Does it have any consequences for seeing something in an experiment today? So for example, this is the classical value of the field, right?
Yeah.
Any fluctuations, any connections, any interaction with standard model fields?
Well, I mean, the fluctuations, it's, you know, the subject of the remaining part of the lectures. So that is a huge connection to the data. Now, in terms of high energy physics, this is a little bit more difficult. Because when you write down a model of inflation, as long as you want to find the prediction for the perturbations, you just need to write down the potential. Now, what happens after inflation, in fact, this is what I would like to discuss even though briefly now, depends on the way this field is coupled to standard model particles or some hidden sector and so on. But you understand very well that there we enter in a very model dependent situation. And you can say many things and being right anyway. Okay, so unfortunately, that part of the dynamics is not very well known. So if you want to connect to the Higgs, for instance, you need to make some assumptions. And assumptions imply some uncertainty, of course. All right? Okay, so if you still have some energy to dedicate to me, I would like to understand what happens at the end of inflation, when inflation ends. Okay, so I want to study, I want to investigate what is going to happen the moment epsilon becomes equal to 1 and inflation stops. Okay? So let's draw the potential that we used before. So phi 0, V of phi 0. So we have a potential like this, which is flat enough, but then at some point the field will start filling the part of the potential which is curved enough, and the inflation will stop. Okay? Epsilon, so at some point, let's say here, epsilon is equal to 1, and then at some point, of course, the field will start oscillating around its minimum. And what is going to do? Well, first of all, I want to write down the equation of motion of the energy density during this oscillation. So rho, if you remember, is 1/2 phi dot square plus v of phi, 0. And now I want to use the following equation. I have to use also the phi double dot because I'm not anymore in the regime where the potential is flat. So I have no right to neglect the phi double dot. Okay? So from here, what I get? I get a rho dot is equal to phi dot phi double dot, 0, plus v dot, which I can write it as v prime times phi dot. Okay? So from here you see that I can collect the phi dot, and I have multiplied by phi double dot 0 plus v prime. Now I can use this equation, and this is nothing else than minus 3h phi dot square. Okay? So far I haven't done any approximation. So I know that during the oscillations of the scalar field around the bottom of the potential, the equation of motion of the energy density is this one. The rho dot is equal to minus 3h times the time derivative square. And now I'm making an assumption, which is very good in any case. It's a very good approximation. I'm assuming that the frequency of the oscillations, so if you like the curvature, or the square root of the curvature, at the bottom of the potential, let me call the v double prime, so which is the mass of the scalar field square around the minimum of the potential, let me call it m. Okay? So this is the mass square, so it's a second derivative of the potential around the minimum. Let me assume that this m square, which always is much larger than the Hubble rate square. This assumption is usually very good in all models of inflation, so let me go on with that, because then I want to make the average over many oscillations in an Hubble time, because if this guy oscillates very, very quickly compared to the Hubble time, I can take the average over many oscillations within a given Hubble time. So I'm going to compute what is the average of rho dot over these oscillations. Let me put OS here. So this is nothing else than minus 3h times the average of phi dot 0 square over the oscillations. But if you remember, if I have an oscillator, you see this phi dot square, you can prove it putting the cosine, for instance, and doing the average over a period, is nothing else than rho itself, okay, because there is equipartition. So this guy is nothing else than minus 3h rho dot, the average of rho, over many oscillations. So from here, so let me now neglect the symbol average and so on. So from here, I get that rho during the oscillations goes like a to the minus 3. So when the scalar field is oscillating, its energy density is diluted away like a to the minus 3, which is like non-relativistic matter. Remember, in non-relativistic matter, rho goes precisely like a to the minus 3. And the reason is, of course, very clear, because you remember the pressure is 1/2 phi dot square minus v. Okay, and if you take the average over of an oscillator of this quantity, the average is 0. Okay, so an oscillating scalar field, which is oscillating around the bottom of its potential with a frequency which is much larger than the Hubble rate, is reshifting its energy density like a non-relativistic matter. It's like a pressureless matter. Okay? Okay, so this guy will oscillate, but at some point, since it will be eventually coupled to other degrees of freedom, it will decay, like the Higgs. Think about the Higgs, for instance. It will decay into lighter particles. Okay, so let's call gamma, capital gamma, the decay rate of this unknown inflaton field. Okay? So gamma is the decay rate of phi. Okay? Of course, we don't know what the decay rate is because it depends on the model. So I cannot tell you is 10 to minus 22 GeV or something. Let's call it just a gamma. When gamma, which is basically 1 over the lifetime of this infraton field, let's put a phi just to remind ourselves it's the phi field, is equal to h, okay? So when tau, the lifetime, is equal to the Hubble time, so the age of the universe, the field can decay, right? Because of course if you have a particle whose lifetime is larger than the lifetime of the universe, it means that it has no decay in that lifetime. So you need to wait for this condition to be true in order for the field to decay. So inflation is taking place, then the inflaton field is oscillating, at some point it will decay, and it will start releasing its energy, its oscillating energy into lighter particles. Standard model particles, for instance. This particle will find themselves in a volume, they will start interacting, they will thermalize. Okay? And let me call T reheating the temperature that this plasma that has been formed out of the decay of the infraton field will reach after thermalization. Okay? So now it's an easy computation to compute this T reheating because I use energy conservation. Okay? So I say that the energy of the infraton field goes into radiation because these particles, I suppose, they are relativistic. So I use the condition that gamma phi square is equal to h square when this process is happening, and I'm also supposing the thermalization is very fast. It's sudden, okay? Of course, you can release such an approximation, but I'm using this here. So all the energy of the infraton field, which is 8 pi g Newton divided by 3 rho phi, they go into radiation. So this is 8 pi g Newton divided by 3 rho of the radiation epoch. Okay? But now what is rho r? Rho r is pi square over 30 g star times T reheating to the 4. Okay? So from here you see that I can derive, if I know gamma phi, I can derive what is the reheating temperature that will be the temperature by which the radiation phase starts. And I know that T reheating will go like the square root of, I read it from here, G Newton is 1 over m Planck square, it will go like m Planck times gamma. Okay? This is the temperature by which the radiation phase starts, and then the usual standard Big Bang cosmology follows. Okay? Unfortunately, we know nothing about this reheating temperature, or almost nothing, because we don't know gamma phi. Why we don't know gamma phi? Because we don't know phi. We don't know what is the infraton field. But we know that there is a lower bound on this reheating temperature, which is 1 MeV, which is the temperature at which nucleosynthesis took place. Light element abundances were formed. And we know the nucleosynthesis is in good agreement with the data, the prediction. So this is, and that happens around 1 MeV. So the only thing that we know for sure is that this reheating temperature is larger than between 1 and 10 MeV. Okay? Other than that, we know nothing. Okay, so when this happens, inflation is finally, the role of the infraton field is finally over, and you can start your evolution of the universe using just standard textbooks. Okay? So this concludes somehow the description of the background evolution during the inflationary period and afterwards. From tomorrow, I will start going back to the space dependent of the dynamics, and we will start the fluctuations part, which is, to me at least, is the most interesting part of the lectures. Okay? I think we can stop here and have a break. Okay, thank you.